Hi and welcome to this next lecture on Introduction to Machine Learning. In today's session we will discuss non-parametric regression and also close some open ends, for example by discussing algorithms for support vector regression and Lasso. So recall that we talked of the kernelized form of support vector regression where all the expressions, the decision function, the optimization function were purely in terms of the kernel. And we had also discussed that one can employ any Mercer kernel in SVR or even the ridge regression with its kernelized dual to implicitly perform linear regression in high dimensional spaces. Recall what a Mercer kernel is. So Mercer kernel is a kernel K such that for any square integrable function g, the integral of gx1, kx1, x2, gx2, dx1, dx2 is positive. So you could try different kernels. We have given examples such as the RBF kernel, polynomial kernel and so on. Try out this applet to see the effect of several of these nonlinear kernels in support vector regression. What we are interested in today is formulations where we adopt these kernel from the word go. So instead of deriving a dual with the kernel, can we define a problem in terms of the kernel? So what we have discussed so far is a basis function expansion, for example f of x as summation over j wj phi jx plus an optional b of course. This is the basis function expansion in the primal space. We discussed the basis function expansion in the dual space. Imagine defining a basis function phi with respect to example xi for point x as k on x comma xi. The alpha i's would then correspond to the weights and we have thus got a basis function expansion for fx through the dual. Now we did this for a very specific choice of the loss function phi w minus y norm square and a specific choice for omega. Let us consider the case of ridge regression 2 norm square. So question is, what about other regularizers? What about regularizers with respect to the q norm square of w? What about other loss functions? In fact very soon we will deal with classification. What about loss functions involving classification loss and so on? What about the L1 loss? So recall that we could also consider the L1 loss phi w minus y L1 norm. Will you get kernelized dual representations for such choice of loss functions and regularizers? So this is of course a subject matter that will require more tools from optimization. What we will do instead is start with the basis function expansion using the kernel in the primal itself. So which means we assume that the function fx is itself some kernel defined over pairs fx comma xi where these xi's are coming from the data set. So we will assume that the data set D is pairs of x1, y1 and so on as we have done so far, but we are involving the data points in similarity with the query point. The alpha i's of course could depend on all the data points. The alpha I is in general a function of the entire data set. An example is the Nadaria-Watson kernel regression model, where the alpha I corresponds to this particular form yi divided by summation over I kn x minus xi norm, and what we have in place of k is something called a non-parametric kernel, and this non-parametric kernel here is basically a function of the distance of x from xi. So we have transformed k of two arguments to a kn of a single argument. This has taken the value of k x comma xi, and we have similarly taken a particular specific form for alpha I. Little bit more about the non-parametric kernel kn. It's a non-negative real valued integrable function in general, which satisfies the requirements that this integral over u of kn u du is 1. So what we are basically saying is that kn u behaves like a density function, a probability density function. In particular, we would like it to be symmetric. So that is symmetric. So we are kind of equally penalizing distances on either side, and you would generally expect these kernel functions to look like this. Non-differentiable at certain points and so on. Now there are many different possible choices for kn, and as we pointed out, it behaves like a probability density function. However, practically you may not always normalize kn, and the reason is that we have kn in the numerator as well as the denominator. So you could think of the denominator as automatically forcing some normalization, especially in the case of the Nadaria-Watson kernel regression. So an example of this kn, which is unnormalized or explicitly unnormalized, is the nearest neighbor kernel, where kn xi comma x gets a contribution from all points that are close enough to the query point, and the proximity is defined with respect to the kth closest point in the data set. So kn xi minus x is 1 if xi is within the k nearest neighbors of x. So this is precisely the nearest neighbor regression model, and in the case of nearest neighbor regression model, the prediction f of x is basically the average prediction of the k nearest neighbors so fx is 1 upon k summation over the k nearest neighbors of yi. So in general, the Nadaria-Watson kernel regression model could be thought of as the weighted average of points, the prediction of points, where the weights are coming based on some distances. Now this is a non-parametric kernel or non-parametric regression model. The reason it's called non-parametric is because the shape of the function has not been decided a priori. So non-parametric because the shape of fx has not been defined a priori. Here by shape we mean a parametrized form. So for example, in linear regression we assume that y is w transpose phi x. Now of course it was linear only in w and not really linear in the input x. The broader class of non-parametric regression is about not making any specific assumptions about the form of the regression function. So you let g of x be kind of determined by the data. The functional form of gx is not fixed. For example, our gx here was this summation over I alpha I kx xi. We will consider another example. So given data set, we need to predict f of x prime for a new query prime. One generalization I make over linear regression is localize it. So localization here has come from the fact that w is a function of the query point. W prime is a function of x prime. So note that phi was always a function of x prime, but now you made even w prime a function of x prime. And how are we doing that? We are saying that we are going to optimize or minimize the loss function for every query point. So corresponding to every query point we find w prime b prime. Now one might ask, well, how does the loss function itself depend on the query point? And here that's how we make the loss function depend on query point. We weigh the squared loss with this kernel. So it's the kernel weighted square loss for each data point. Now, is there a closed form expression for w prime, b prime? If yes, then we would like to derive it. How does this model compare with linear regression and say k nearest neighbor regression? What are the relative advantages and disadvantages? These are questions to be asked. And can we try and graphically interpret? Because that's something we would like to do not only for local linear regression but also for nearest neighbor regression. So the answer to the first question is fairly simple. All you need to do is associate weight matrix. This weight matrix has been associated with all the data points and there is a weight corresponding to every input data point along the diagonal. The query point x prime is fixed. So this is an m plus 1 by m plus 1 diagonal matrix. What we have done is also padded the b. So the b is padded, or component for b. So recall that this is a trick we have often employed to simplify the derivations, and that's what we have done here. We have also associated a dummy feature 1 to accommodate the b. What next? Well, we now rewrite the sum of square error function, and well, we have the weight Ri sitting here. Now you could easily show that this sum of squares weighted by Ri could be written as the norm of this vector, norm square of this vector, where both components are pre-multiplied by the square root of r. So this is the overall sum of squares error function. You can actually compute a global minimum by setting the derivative to 0 and also verifying that the Hessian is indeed positive semi-definite. And it turns out that this is a very simple variant of the general least square solution. Instead of a phi transpose phi inverse phi transpose y, we have an r sitting in between the two phi's. So the effect of r has been through the square root of r, which gets pre-multiplied with phi. So this is effectively replacing phi with square root r times phi, and we also replaced y with square root r times y. So basically this is how we weigh each example. We have weighed the input and the output both. So second question is how does it compare with nearest neighbor regression? So for example, local linear regression gives more importance to points in the data set that are closer or similar to x prime and less important to points that are less similar. Thus, in contrast to linear regression, it kind of localizes the whole process of curve fitting, and therefore it is useful if the regression curve is supposed to take different shapes at different parts of the space. So for example, if you expect points to behave like this here and points to behave slightly different in a different location, you might be happy to find a curve fitted this way by local linear regression because it just didn't make any prior assumptions on the form of the overall curve. It made a linear assumption for each query point, but overall you didn't make any specific assumption. This is its similarity with and difference from linear regression, but how about k nearest neighbor? Well, k nearest neighbor only looks at the k closest neighbors. So k nearest neighbor is a non-smooth, whereas local linear regression gives you a much smoother solution. It interpolates between points that are far away but gives them less weightage. So here is the plot with a polynomial fit, a green curve. Well, you do find that the curve is often not bending its way in order to satisfy all points. The red one is local linear regression, and you find that lots of bends may or may not be desirable in specific situations, but yes, if you can afford the cost, local linear regression isn't bad. The cost or the price you need to pay is fitting for every query point. Of course, there are other non-parametric regressions which aren't so expensive, but they may not be as effective. Let's move to the support vector regression problem now and see if we can solve the optimization problem. So recall that we had left at the support vector regression dual optimization problem. This is a linearly constrained quadratic program. We are interested in whether we can actually solve this. Well, there are lots of solvers. Linear constraints are basically what you see here. The quadratic program is the maximization problem. LCQP, as it's called, has several standard solvers. There is no closed form solution to this formulation. There are several standard QP solvers. The question, however, is are there more specific and efficient algorithms for this form? It turns out that our linear constraints are very interestingly simple, and maybe we can come up with a customized algorithm that can very effectively handle these somewhat simple constraints. And indeed, So sequential minimal optimization algorithm, which is also known as the SMO algorithm, is one such algorithm for solving support vector regression problem, and in general for the support vector optimization problem, which will also surface when we look at classification. The idea here is as follows. We first of all substitute for alpha I minus alpha I star as a single variable beta I. So you find that all the occurrence of alpha I or alpha j minus alpha star could be absorbed. Well, what remains is this particular term alpha I plus alpha I star. Now it turns out that since between alpha I and alpha I star one of them will be 0, the other non-zero, so the sum of alpha and alpha I star is nothing but the absolute value of beta I. So you can show that alpha I minus alpha I star's absolute value is nothing but alpha I plus alpha I star, since one of them is 0. The rest is fairly straightforward. Question, however, is how do you solve for the absolute value of beta I? Again, there are tricks to handle this. You could add constraints and get rid of the absolute value. But modulo that, how do you solve this optimization problem? It turns out that you can hold all beta i's constant except 2. You need to keep two of the beta i's variable, because you want the sum of all the beta i's to be 0. So the idea here is, if you pick beta I and beta j, then you need to keep beta I plus beta j is constant and optimize across iterations. The constant is obtained from the values of beta I and beta j from the old iteration. So beta I new plus beta j new is constant old. That's the basic idea. And this is the idea of the sequential minimal optimization algorithm. So this is the idea. Initialize beta i's to some value between minus c and c. So recall that alpha I and alpha I star are between 0 and c, which implies that beta I should be between minus c and c. So you pick some two arbitrary beta i's, beta j, and form the new iterates beta I new and beta j new as pointed out earlier. So you will need to write the entire optimization problem in terms of only the two beta I and beta j. So beta I new and beta j new will turn out to be arg max of some quadratic form, which is ai square beta I square, the arg max or beta I beta j, plus aj square beta j square plus aij beta I beta j plus some constant c, which will be a function of other betas and the epsilon and so on. So it can be ignored. So basically it becomes an optimization problem in two variables, and even with that, if you use that beta I is the constant from the old iteration, constant old minus beta j, you could actually solve this as a function of a single variable. So the closed form solutions could be easily found. The only thing is you need to project back the beta i's and beta j's to this closed interval minus c to c. The next thing you do is check if the KKT conditions are satisfied. If yes, you are done. If the KKT conditions are not satisfied, you choose a beta I and beta j that worst violate the KKT conditions and continue the iteration. We will quickly discuss the algorithm for solving the Lasso problem as well. So recall the Lasso problem, where we were trying to find a W that minimizes the sum of squares error with the constraint that one norm of W should be bounded. Now the one norm is not differentiable, so what we can do is express the second constraint in the form of set of constraints including new xi I. So xi I is basically upper bounding the absolute value of Wi, and it is stated by upper bounding Wi as well as the negative of Wi. Now it turns out that the new problem doesn't have the absolute sign or the L1 on the norm on W, could be actually solved as a linearly constrained quadratic optimization problem, the way we discussed for SMO. It's a much simpler problem though, and you can show that the two are equivalent as follows. You can show that 1 and 2 put together gives you the same solution as 3, and here is how we can quickly show this. Well, if W star were a solution to 1 and 2, then my claim is the same W star will be a solution to 3. Of course, what we also need now is the value of xi I. So my claim is W star and xi I set to the absolute value of Wi star is solution to 3 if W star is solution to 1 plus 2. It's easy to see because the objective in 3 does not involve xi I at all, and all you need to make sure is the constraints are satisfied, and indeed the constraints are satisfied. The objective is exactly the same. We can also show that any solution to 3 is also solution to 1 and 2. In fact, the multiple solutions possible to 3, and all you need to do is ignore the xi I. We already know that xi I star, which is obtained as a solution to 3, is less than equal to eta, the summation xi I star, and we know that xi I star upper bounds absolute value of Wi, which implies that the summation of the absolute values of Wi will also be upper bounded by eta, that is the L1 norm of W, will basically the W star will be upper bounded by eta. So this just proves equivalence. We can now write the KKT conditions. We have introduced Lagrange multipliers, theta I for Wi less than equal to xi I, lambda I for minus of Wi less than equal to xi I, and one more Lagrange multiplier beta for summation xi I less than equal to eta. And these complementary slackness conditions have been written down. You could actually show that the equivalent Lasso formulation can be obtained by adding a penalized version of the L1 norm of W to the original loss function. Now this requires some more machinery showing the equivalence of 4 and 2. It basically requires analysis through subgradients. What we will do instead is look quickly at the optimization algorithm for Lasso, an optimization algorithm that is again born out of subgradient based descent analysis and also includes a notion of projection. So we will quickly see what that projection means. So specific algorithm is called iterative soft thresholding algorithm, and as I pointed out, it is basically a special case of proximal subgradient descent, which I have left as extra reading material in case you are interested. The idea is as follows. Imagine the unconstrained problem. You want to minimize the error, find a starting point, let Wk plus 1 hat be next iterate for epsilon, the error function at Wk, but computed using any gradient descent algorithm, and that is the key. The key is basically that you remove the constraint, apply a standard gradient descent algorithm, so that gives you Wk plus 1 hat, and now you are going to find that Wk plus 1, the constraint version that is closest to Wk plus 1 hat. You have actually gotten rid of the phi and the y, but you want it to be close with respect to the penalized, the regularized, penalized the L1 norm of W. Now the solution to this turns out to be as follows. The solution is that if your wk plus 1 hat is greater than lambda t for the step size t, then the closed form solution is wik plus 1 should simply be minus lambda t plus wi hat k plus 1. So what you are saying here is, if wik plus 1 hat is large, shrink. So shrink large values of wi hat k plus 1. The other step is just saying, if wi hat k plus 1 is small, expand it, grow it, grow small wi hat k plus 1. Of course you are growing it in a way that you do not violate the constraints. This is called iterative soft thresholding. You are basically iterating, finding the next iterate, but you are subjecting it to a soft threshold. Thank you very much.